Right. Welcome to our last, but by no means, final, but by no means last session of the day, where we got Dr. Matloob Khushi he's a senior lecturer in AI at the University of Suffolk. He's going to talk to us about the fourth age. And I know in some other industry settings, you've got Industry 4.0 in manufacturing. You got, 5G, now they're talking 6G in the mobile world. But I can just see this kind of thing developing in terms of the AI and ML area as well over time. So, Dr. Khushi, over to you. Everything we wanted to know about the fourth age.
Thank you very much, Mike. And thanks to the organizers for giving me a chance to speak today. So I'm going to talk about this AI, the fourth age. And what do I mean by the fourth age? So the fourth age means the way artificial intelligence has been transforming our lives nowadays. We can see a similar trend that happened in the previous ages when the society transformed from Stone Age to the Bronze Age and then the Iron Age. We've seen a radical change in the way people interact, the way people used to live, the way people used to do their business. The whole society have been transformed during the change of this era. But similarly, in the AI, it's been changing our lives much faster than ever before. I'll give you a quick example. Like recently, I visited to Poland, and many of the common people in Poland on the street, they don't speak English, and I don't speak Polish. So we have now apps that can translate from one language to another app, and these are the conversational app, and they work beautifully well. And now that means the language is no more a blocker between interacting from one community to the other community. And similarly, the way we seeing our computational approaches and the way we do our businesses and the way we doing our handling of all of our affairs. And now in some of the cities, we've seen automatic cars that's been driven, taking you from point A to point B. That's been already trialed in quite a few cities, and it's expanding. And the main thing is like we in a single lifespan, we've seen so many changes, so many things happening, and that's all due thanks to the artificial intelligence. So, what's my contribution? I'm going to be talking about a little bit of my tiny contribution in this space of artificial intelligence. And the first project that I would like to talk about is dealing with the class imbalance problem. So, why this is very important? Because many times, like I'm sure everybody is aware of how the artificial intelligence works. You train your artificial intelligence or machine learning algorithm on an existing data, and then you apply that to your future data. But if there are some biases in the data, so that means our machine learning or artificial intelligence, whatever method we've been using there, will have the inheritance biases in the data. And one of the very common problem that we see, and especially that's very common in medical data sets where we have a huge number of samples from one sample. For example, you have so many normal patients and only few develop the cancers or the disease that you're looking at. So that means you have a heavy class imbalance, like the number of samples in one class are really large than the number of samples in the class that we are really interested in. So that means whatever machine learning algorithm we're going to be applied, if we not take into account this bias in the data, it's going to inherently learn to predict every person coming into our clinic as a normal person and probably will never predict a patient. So as an example, the data set that lately worked with, we obtained from ovarian cancer from a data set from PLCO, NCI. And as an example, you can see nearly 38,000 normal people and only 277 cancer patients in there. So, I mean, this is a well-known problem everybody is aware of, and the people, the the way people like to manage it. There are various ways you apply that on an algorithm level. Three major methods by which you deal with this problem. One of them, on an algorithmic level, you try to address that into your ML pipeline, or you do it on a data level, like you increase your number of samples artificially, which is called oversampling, when we have a very common method for that called smooth synthetic, which synthetically basically increase your number of sample, or you do your undersampling, like you randomly select some of the samples matching with your smaller class. Um, and that's one of the way you can implement, or you can do a little bit of hybrid system where you do a little bit of algorithmic approach, implement some of the data level, increasing your number of samples or selecting smaller number of samples from a bigger class. So you do that. So there are like almost 23 methods out there that's been published in the literature. So in one of this very recent publication, we show this whole pipeline. We show the best practices, how to work it out. What's the best method that could work on a medical data? And one of the main problem that that at least I have seen in many of the papers, some of the research paper not really clear about that. How did they implement their class imbalance method on the test data? And to be just very clear, the way we should be doing it, when we sample the training data, so we inflate it, we increase it, decrease it, whatever you do it. But when we do the evaluation on the test class, we don't do anything to this data set. So that's very important, which is sometimes not very clear in some of the research papers, or even I've seen some research paper which do it for me, like it's a wrong method to touch anything on your task data. Like we're not meant to inflate this testing data, so it just use it as it is in its original form. So in all of these methodologies, if your samples have a nominal data, so what do we mean by nominal data? Like you could have a feature such as male or female, that's a categorical data, or it's also called nominal data. Or you have a Likert type scale, like you could have a feature where you say, okay, how much do you like this particular product, and your features could be, your data could be like from 1 to 5, so you have a number in there. So that when you have that sort of data set, then these like many major methods don't really work well. And the only method that we have to address this kind of data is called smooth NC. But that, again, not really, it doesn't really work well on many data sets. So, so what we have done lately, we contributed a new method in this space. We're calling it a smooth ENC, encoding the nominal and continuous features. And we show its efficacy on 4 major data sets that are well known in this space. And we show when we have a nominal features and we have a continuous feature mixed together, then our method outperforms the existing well-known method, which is smooth NC. And we can see in the last column, the F1 score in all of these cases for our method, which is smooth ENC, is better than the smooth NC, the existing method. And as a matter of fact, like smooth NC is not designed to work only on the nominal features. When your data set only have a nominal features and no other type of feature, then basically we don't have any existing method out there. So our design methodology work on this type of data as well, and it gives like pretty good performance. In this case, it was 83.3% as the F1 score. I'm not really going into much details about how this methodology works. So that's been explained in this research paper people are interested in, they are welcome to have a look to the paper and make use of the methods. The method is available, like we released the code in open source space as well. So the another project in this artificial space I like to share you that one of my PhD student is working on is estimating the blood pressure from some sort of easy method rather than the conventional cuff-based method. So why the blood pressure is important? It's an indicator for many of the underlying diseases. As we know, we could estimate coming up a heart problem, brain problem, or some problem with the vessels, kidney or eye problem. Lots of underlying diseases could have some relationship with irregularities in the blood pressure. And as we know, the existing blood pressure method is a cuff-based method, and you can only take this measurement as a discrete data points. You cannot measure it as a continuous feature. So if we have some ability to measure someone's blood pressure continuously 24/7, so that means we could develop some more artificial intelligence methodology to predict coming up disease problem or heart problem or anything. So we're working on this, designing this watch. The way this watch, a watch type gadget, the way it works, we have a 2 ppg sensor which shines light on the blood vessels and then note the change of the blood coming up. And what we're trying to measure the very tiny change from the difference in the blood movements when it passes from the location 1 to the location 2, and we have 2 sensors here, and these are some of the plots that we have from these 2 locations. So it's very hard to see with the naked eye that there is a very subtle change in the blood pressure measurement that's happening here from one location to another location. But because the way we have designed our artificial intelligence methods, they can pick up that very subtle change in the blood pressure. And one of the methods we published in this paper show the efficacy of our methods. So we hope that by designing this watch, we could implement, we could do a continuous blood pressure measurement. And the final project I'd like to share with you quickly is the modeling the financial markets. We can see the financial markets radically change, go ups and down, but they do that in a kind of wave fashion. So we can pick up these changes in the, because for us as ML or data scientists, these are just signals, and we can see the coming up waves going up and down. And this is again our paper that's being published, one of this paper where we're modeling the Forex market, and another paper where we've again modeling the Forex market, but then also taking into account the risk factor, the portfolio management, and implementing some genetic algorithms. Again, the details of the papers are here. And we show that by implementing these methodology, we can outperform a lot of other trading methodologies. So I kind of stop here. I know we're not going to take a question, so we leave the question during the panel discussion. So thanks, Mike, for listening.
Dr. Khushi, thank you very much for that session. Once again, lots of really fantastic insights. And just a reminder, Dr. Khushi, you have to come out of the current Zoom session and log back in on the Teams session for the panel discussion here in just a moment. So what I'll do is I'll bring this session to a close, and I'll see you with the panel discussion in just a moment. You don't want to miss this. This is a really heavyweight panel of AI and ML experts at the end of the day, so there should be some really fascinating insights coming out of it. So see you there in a minute.